Chapter 2, Water and Carbon, the Chemical Bases of Life. In this chapter, we're going to talk about the structure of atoms, ions, and molecules. And from there, we'll find how atoms bond to other atoms and molecules and how reactions occur. And then we'll discuss the properties of water. And the last part of this chapter is talking about chemical evolution and how this leads to the role of carbon and organic chemistry. Chemical evolution. What does it mean? When we talk about chemical evolution, what are we talking about? It simply means going from small molecules to the formation of increasingly complex molecules. And this is the explanation of the origin of life on Earth. In other words, there had to be a chemical evolution before there was a biological evolution. So the tipping point is to find a molecule that could replicate itself. After the formation of a replicating molecule, then evolution by natural selection took over, and this is where we have the beginning of the first cells and the 5 characteristics of life that we discussed in Chapter 1. In this chapter, we'll be talking about atoms, ions, and molecules, and how these are the building blocks of chemical evolution. So the 4 important atoms that you need to know, and it'll be on your next test, is hydrogen, carbon, nitrogen, and oxygen, because it makes up 96% of matter in organisms. So the question is how did simple substances evolve into complex structures in living cells? What is the physical structures of hydrogen, carbon, nitrogen, and oxygen that made them so accessible to go from simple molecules to forming really complex molecules that are carbon containing? And that's what the chemical evolution is all about. So what is the basic structure of an atom? The 3 subatomic particles are protons, neutrons, and electrons. Protons have a positive charge, or +1. Neutrons have a neutral charge, and electrons have a negative charge. Protons and neutrons are found in the nucleus of an atom, and orbiting around the nucleus are the electrons. Atoms with an equal number of protons and electrons are charged balanced and therefore electrically neutral. If you take a look at figure 2.1 in the diagram, you see hydrogen and carbon, and you see that hydrogen only has 1 proton in its nucleus and 1 electron orbiting outside in the first shell. On the other hand, carbon has both protons and neutrons in its nucleus, and in its first shell there's 2 electrons orbiting around, and in the second shell there's 4 electrons orbiting around the nucleus. The best analogy that you can give is the atom, the nucleus, is like a football on the 50-yard line, and the electrons are orbiting around just like the seating in a stadium. Every element on the periodic table is unique, and what makes it unique? It's the number of protons. It is actually the number of protons, and that sounds like a great test question. The mass number is the number of protons and neutrons, and remember, protons or neutrons are found in the nucleus. If you look at a periodic table, you're going to see in each of the squares there's a symbol. H is for hydrogen, C is for carbon, N is for nitrogen, and O is for oxygen. And you're going to see 2 numbers, a large number and a small number. The large number is typically the mass number. It's the number of protons and neutrons. And the atomic number is the number of protons. Remember, the number of protons makes each element unique in the periodic table. You know how I remember C-H-O-N. I always think of Chon, like Cheech and Chong, but I just say to myself Chon. So those are the elements that you should really know, the atomic number and their mass number. Each proton and each neutron has a mass of 1 Dalton. The mass of an electron is so small that its mass is negligible. Therefore, when we talk about the mass of an atom, we're really just talking about its atomic mass. In other words, the number of protons and the number of neutrons found in the nucleus. Now, surprisingly enough, the number of protons in every element does not vary, but the number of neutrons and actually the number of electrons can vary. When the number of neutrons starts to change, we call that an isotope. Iso means similar. It's not identical, it means similar. So it's the same element because the number of protons are the same, but the neutrons are different. And because the number of neutrons are different, then the atom has a different mass. The classic example is comparing carbon-12 to carbon-14. Remember, carbon-14 is used for dating fossils, and that's because the neutrons actually can decay over time, and that's how scientists can actually date fossils. So in carbon-14, instead of having 6 neutrons, there's actually 8 neutrons, and its mass is 14 Daltons. So when we look at the atomic weight, like if you look at a periodic table, how is it that the atomic mass or the atomic weight is not a whole number? It's usually a number past the decimal point. For example, carbon, it's 12.01. And the reason is that scientists have taken averages of all the masses of naturally occurring isotopes based on their abundance, and then they take an average, and that's why you see a number past the decimal point. Keep in mind some isotopes are more stable than others, but when we say that we have a radioactive isotope, it usually indicates an unstable isotope that will decay over time. For example, carbon-14. The most abundant elements of all time are carbon, hydrogen, nitrogen, and oxygen, and also phosphorus and sulfur. So keep in mind Chon represents 96% of all what's in life, and if we add phosphorus and sulfur, P and S, it makes up over 99% of all atoms in our body. I love this periodic table. I love figure 2.3. And 2.3 represents the first 3 rows of the periodic table. But for this class, and for most biology classes, the first 3 rows of the periodic table are the most important. And why is that? Because it contains Chon, C-H-O-N-N, and then also phosphorus and sulfur. And so the first 3 rows contain what makes up 99% of all life. I also like that it shows the number of electrons orbiting in each of the shells. Notice the first row has 1 shell. Notice the second row has 2 shells, and the third row has 3 shells. Notice the octet rule. Notice that, except for the first shell, which only holds 2 electrons, shells 2 and 3 can hold up to 8 electrons. Electrons travel in orbitals, and orbitals are just 2 electron pairs. So the first shell has 1 orbital, but the second and third shells can have up to 4 orbitals, or a total of 8 electrons, because 4 times 2 is 8. The electron shells are numbered 1, 2, and 3. Shell 1 is closest to the nucleus, then 2, and then 3, and so on and so forth. Each electron shell contains a specific number of orbitals. Electron shells comprising single orbitals can hold up to 2 electrons. So, shells 2 and 3 can hold up to 4 orbitals or up to 8 electrons. Electrons of an atom fill the innermost shells first, and then shell 2, and then shell 3, and so on and so forth. The outermost shell is called the valence shell, and that valence shell is so important because the valence shell indicates how reactive an element or an atom is going to be. So, the valence shell is the outermost shell, and the electrons that are in the outermost shell are called the valence electrons. The number of unpaired valence electrons is called the valence of an atom. Another way of seeing it is how many more electrons will it take to make 8, and that will also give you the valence. So you can look at the number of unpaired valence electrons or say to yourself, how many more electrons does that shell need to fulfill the octet rule? Atoms are most stable when their valence shells are full. So to have full valence shells, they're going to form chemical bonds. And one type of bond is called a covalent bond. And the operative word for a covalent bond is the sharing of electrons. So covalent bonds form when unpaired valence electrons are shared by 2 atoms. Connected atoms are termed a molecule. Atoms become very stable by making covalent bonds. Hydrogen does not have a full valence shell, so 2 hydrogen atoms can share electrons. The outer shell is filled and it becomes more stable. In this example here, you see 2 hydrogen atoms, and each of these hydrogen atoms, the first shell needs 2 electrons to become stable. So each of these are needing 1 more electron. If they form a covalent bond and they share the electrons, then it fulfills the number of electrons in the first shell. So hydrogen gas, which you see on the right-hand side of your screen, is much more stable than 2 hydrogen atoms. What is a compound? A compound forms when electrons in covalent bonds are not always shared equally, and compounds are molecules in which atoms of different elements are bonded together. And so they can pull shared electrons towards each other, and this creates electronegativity. And when it does, this will form polar covalent bonds. So here's an example in figure 2.5 of either a nonpolar or a polar covalent bond. And in the first example, 2 hydrogen atoms are sharing their electrons evenly. They're sharing them in the middle. So because of this, it is a nonpolar covalent bond. Water, on the other hand, has oxygen, and oxygen is extremely electronegative, and it's pulling the electrons towards oxygen, and electrons have a negative charge. And because they have a negative charge, then the oxygen side of water is negative. Hydrogen is only left with a proton in the nucleus, and protons have a positive charge. So the hydrogen side of water has a partial positive charge. What do we mean by electronegativity? Electronegativity is the strength in which atoms pull electrons towards themselves. electronegativity is determined by the number of protons, but in general, oxygen is very electronegative, followed by nitrogen. Sulfur, carbon, hydrogen, and phosphorus are not electronegative. Nonpolar covalent bonds means that electrons are shared evenly between two elements. A classic example is carbon and hydrogen. In a polar covalent bond, electrons are shared unevenly or asymmetrically, and electrons in polar covalent bonds spend most of their time close to the nucleus of the more electronegative atom. For example, if we remember water, oxygen is electronegative and the electrons spend most of their time next to oxygen. What are the consequences of differences in electronegativity? If we have oxygen, which is electronegative in water, then one side of the molecule will be negative, the other side will be positive. We can say that there's a partial negative charge and a partial positive charge. And we use the symbol delta, delta negative, and delta positive to indicate that water actually acts like a magnet. There's a negative side and a positive side. Now, another type of bond is an ionic bond. And in this case, the electrons are not shared, they're actually transferred. So they're transferred from one atom to another. So if an atom loses an electron, it is called a cation, and it becomes positively charged. Why is that? Because remember, the number of protons and electrons are balanced in an element. So if it loses an electron, that means that there's more protons. And because of that, it has a positive charge. You know how I remember that cations have a positive charge? There's a T in cation, and that T reminds me of positive. An anion gains electron, and electrons have a negative charge, so the overall charge of an anion is negative. A classic example of an ionic bond is that between salts, and the most common one of all is sodium chloride. Sodium chloride crystals are what we have on our table to salt our food to make it taste better. If you look at sodium, sodium has one lone electron in its outermost shell. That means it would need 7 more electrons to become stable. But it's much easier for sodium to transfer its single electron in its outermost shell to chlorine. Chlorine already has 7 electrons in its outermost shell, and it needs 1 more. So now they both become satisfied. They become stable in the transfer of electrons. Now, unlike covalent bonds, ionic bonds, when you transfer electrons, are very weak bonds. The degree to which electrons are shared in chemical bonds forms a continuum. And the strongest bonds are nonpolar covalent bonds. Next are polar covalent bonds, and then the weakest bond would be an ionic bond. In figure 2.7, we see the electron sharing continuum. On the left-hand side, hydrogen gas and methane have nonpolar covalent bonds, and therefore they have very strong bonds. But notice at the opposite end, the transfer electrons in ionic bonds, these are weaker bonds, and they can dissociate very easily, especially in water. Each unpaired electrons in valence shell can make up half of a covalent bond. The number of unpaired electrons determines the number of bonds an atom can make. Now, we know that one covalent bond consists of two electrons, but you can have double bonds and triple bonds. In a double bond, you have two single bonds, so that's a total of 4 electrons, and a triple bond is 2 times 3, which is 6 unpaired electrons. In figure 2.8, you can see some examples of single bonds, double bonds, and triple bonds. Water and ammonia, NH3, are classic examples of single bonds. But look at CO2, carbon dioxide. Notice carbon is sharing 2 electrons on 2 pairs of electrons with oxygen, forming double bonds. And look at nitrogen gas. Nitrogen gas is actually sharing 3 electrons. And so these 3 pairs make up 6 electrons total for a triple bond. Molecule shape often dictates its behavior, so the geometry of a molecule is really important. But in this class, I will be happy if you understand the nucleus and the electron shells. We'll leave the geometry for a chemistry class. So I'm going to move on to the next slide. And in this one, you can see the geometry, but remember, you won't be tested on this in your next exam. Okay, now, it is important to know that we can represent molecules in different ways. One way of doing it is a molecular formula. H2O means 2 hydrogens and an oxygen, and you guys know that it forms water. Methane is CH4, 1 carbon and 4 hydrogens. We can also indicate the relationship between atoms in structural formulas or in ball and stick models or space filling models. I love figure 2.10, and it shows you how we can represent molecules in different ways, as a molecular formula, a structural formula, ball and stick models, or space filling models. Water is a very important part of chemistry, and just like CHONN, most life is 75% water. So every cell is 75% most likely is water. Water is an excellent solvent. Solvent is the liquid part of a solution, and dissolved in a solvent is a solute. So solutes are dissolved in a solvent, and the two of them together make a solution. So for example, if I'm making spaghetti and I put salt in my water and boil it, the water is the solvent and the solute is the salt, and the two of them together is a solution. Another example would be coffee in the morning. The solvent is water, the molecules of coffee is the solute, and the two of them together is the solution, especially when you put in sugar and cream. Water is unique because of its small size, its bent shape. It has highly polar covalent bonds, and it's highly polar, which means it's like a magnet. You know, like the magnet that you find on your refrigerator. It has a positive side and a negative side. So the oxygen side of water has a negative charge. The hydrogen side of water has a partial positive charge. And because of this, water likes other charged molecules. Birds of a feather flock together. So water likes charged particles. Now, another important thing about water is that it forms a third type of bond, and this type of bond is called a hydrogen bond. So what is a hydrogen bond? It is a weak electrical interaction between hydrogen of one water molecule and oxygen of another. So let's take a look at this. I love figure 2.11. First, it shows you that water is highly polar. Notice the oxygen side has a partial negative charge, and the hydrogen side has a partial positive charge. But what's a hydrogen bond? Excuse me, you can see this in part B. You can see the dotted lines highlighted in yellow. That is the hydrogen bond. Notice that hydrogen is part of the hydrogen bond, and it's a weak electrical interchange. So the opposite of positive from hydrogen is negative, which is oxygen. And that's why you see all of the hydrogen parts attracted to an oxygen of a second water molecule. A term to describe that is hydrophilic. Hydro means water and philic means loving. So hydrophilic means water loving. So hydrogen bonds can also form between water molecules and polar solutes. In other words, birds of a feather flock together. So water loves charged molecules. Ions and polar molecules stay in solution due to their interactions with water. We consider that hydrophilic. Hydrogen bonding makes it possible for almost any charged or polar molecule to dissolve in water. In this example, you can see, like the spaghetti water, why is it that when you put in salt into water, it dissolves? Well, because the water starts circling sodium and chlorine molecules. Remember, the opposite of a negative charge is a positive charge. So oxygens are attracted to sodium. And then the hydrogens in water are attracted to chlorine because opposite charges attract each other. The opposite of hydrophilic is hydrophobic. Hydro meaning water and phobic meaning hating or fearing. Hydrophobic. So water doesn't like uncharged or non-polar compounds. You know, those kinds of bonds that you've seen between carbon and hydrogen. Hydrophobic interactions occur in water because there are situations where water does not interact with those molecules that have no charge. And so van der Waals is one type of these interactions. So now you understand why when you have oil in your salad dressing, why you see globules and it doesn't mix with the water, because oil are non-polar compounds and water is charged. So it's a hydrophobic interaction. Or another example is an oil spill in the Gulf of Mexico. Why is it that it doesn't dissolve in the water? Why is it that you still have an oil spill? Because oil has no charge. They are non-polar covalent bonds. The electrons are shared equally, and because of that, they have no charge. And water is only attracted to other molecules that have a charge. In this example here, in figure 2.13, you see that nonpolar molecules, those in silver and black, they share the electrons equally in their bonds, and they have nonpolar covalent bonds, and therefore they do not interact with water that is charged. Cohesion and adhesion. Another property of water is that it's attracted to itself, and it's attracted to other molecules. Sometimes I get them confused, but I always think of adhesive strips or band-aids. So, that means the attraction of water to other molecules, and cohesion means the attraction of water to itself. So water is cohesive. It is attracting to itself. So water molecules attract to each other and they connect through hydrogen bonds. But they also are attracted to other things too. So they have high adhesion. They adhere to other molecules, like for example, if you're pouring water into a glass jar or plastic jar, water is attracted to the walls of the glass. When water is attracted to each other in cohesion, it creates surface tension. And this surface tension causes water to bead up. So water resists any force that increases its surface area, and therefore it makes this elastic membrane. Because of this elastic membrane, you have spiders that can literally walk on water due to surface tension. And here you see the formation of a meniscus in a glass tube because of both cohesion and adhesion. Notice that water's sticking to the sides, and so it's climbing up the sides of the tube, but it's pulling down in the center because of cohesion. Water is denser as a liquid than it is as a solid. And I think this is the only substance that I know of that is actually denser as a liquid. So it's denser as a liquid than as a solid, and you know this because ice floats. If you have an ice cube, it floats on the top. And so this is really important to life as we know it. Wouldn't it be terrible if ice sank to the bottom? If it sank to the bottom of the oceans, then the rays from the sun wouldn't be able to melt the ice that it sunk to the bottom of the ocean. And so then the water would always be in the form of ice. And then life would have never formed in water. And then from there it would have never evolved up into land. So this one trait is critically important to the evolution of life as we know it. So why is it that hydrogen bonding in ice is different from water? As you can see here, it actually forms a crystalline structure, and the hydrogen bonds extend from themselves and become less dense. And in the liquid form, you can see that water molecules are packed closer together and the hydrogen bonds are shorter. And for this reason, ice floats. For this reason, you can have ice crystals and snowflakes. I always wanted, that was part of my bucket list, was to actually see a real snowflake. And a couple of years ago, I actually saw one land on my windshield of my car. So that was exciting. The next thing I need to see is an iceberg. Water also has a high capacity for absorbing heat. So water has high specific heat. That means the amount of energy needed to raise temperature by 1 gram of a substance by 1 degree Celsius. So water has very high specific heat because it has many hydrogen bonds. And these hydrogen bonds will need to be broken for water to move much faster. And for this reason, water has high specific heat. It's those hydrogen bonds. If you compare water to other forms or other solvents, you can see that because of the multitude of hydrogen bonds, water has a tremendously high specific heat compared to ethanol, glycerol, benzene, and xylene. Heat of vaporization. Heat of vaporization is the amount of energy required to change 1 gram of a substance from a liquid to a gas. And water has a very high heat of vaporization. In other words, it takes a lot of energy to convert water from a liquid to a gas, and we intuitively know this. An engineer once told me that it's fascinating to come to the desert where it's over 100 degrees Fahrenheit, and you see children coming out of a swimming pool and they're freezing cold. Well, why are they freezing cold when it's over 100 degrees outside? And it's because of the heat of vaporization. Water is, that conversion of water from a liquid to a gas is stealing the heat from the surface of our skin. And when it does, it's using that thermal energy that to break the hydrogen bonds. We have a cooling effect. And we use this for evaporative cooling. And you know what? You know those clay jars that you can get in Wadis, those pitchers of clay and the clay jar, the water from them are very cool. And this is because the heat of vaporization. Hydrogen bonds are broken, and when it's broken to convert water from a liquid to a gas, it absorbs a lot of energy. And this is why sweating is also an effective way to cool off. When we look at water, we also have to think of pH. And before we can start talking about pH, the power of hydrogen or acid-base reactions, we just need to talk about what is a chemical reaction. Keep in mind a chemical reaction is breaking bonds and forming new ones. So a chemical reaction has two parts to it. It has on one side reactants and on the other side products. So one classic example is water, H2O, but it can be broken down into hydrogen and OH, which is a hydroxyl group. And notice both of those are ions because you can see that they're charged. The hydrogen is a cation and the OH is an anion. The degree into the way that water breaks down is how our acid-base chemistry scale is built. That's why our pH scale goes from 0 to 14 because it's related to this dissociation of hydrogen and OH in water. When we think of an acid, we think of a substance that is donating hydrogens. Another way of saying hydrogen is proton. Why do we say that H plus is a proton? Because it's lost its electron, right? It's given it to the OH group, and all that's left is a proton in the nucleus. So H plus is often called a proton. So by definition, an acid is any substance that gives up protons during a chemical reaction. Adding an acid to solution increases the number of protons or the proton concentration of the solution. A base acquires protons, so adding a base to solution will decrease the proton concentration. How can we determine the concentration of protons? Well, we have to go back to what is a mole. And a mole is Avogadro's number. That's 6.022 times 10 to the 23rd. And so it's the mass of 1 mole of an atom, and its atomic weight is expressed in grams. So the molecular weight is the mass of 1 mole of a molecule. Molarity is the concentration of a substance or the molecular weight in solution. So it's the number of moles of solute present per liter of solution. Okay, so now that we know that the concentration of protons in water is very low, it's 1 times 10 to the negative 7 in molar. And so this is how we get this logarithmic scale. pH, the power of hydrogen, and literally it's 2 base 10. It's a logarithmic scale. So that power of hydrogen refers to its logarithmic notation. Excuse me, 1 pH unit represents a change in concentration of hydrogen ions equal to a factor of 10. Acids have a pH of less than 7, bases have a pH of greater than 7, and a neutral pH is a pH of about 7. A buffer resists change in pH, and that creates a chemical homeostasis. If we look at figure 2.16, we see that pure water has a pH of 7. You can see in this scale here that water has a pH of 7. But if you take a look and you take a look at lye, it has a pH of 14, and stomach acid and lemon juice have a pH of 1 and 2 respectively. Chemical reactions, energy, and the chemical evolution. Two environments where chemical evolution may have begun is either in the atmosphere or in deep sea hydrothermal vents. In the atmosphere, you have water vapor, CO2, nitrogen, and small amounts of hydrogen and carbon monoxide. In deep sea hydrothermal vents, you have hot rocks, carbon dioxide, and hydrogen gas. Most reactions occur when there's a mixing of gases, and a classic example could be from volcanoes. So one type of reaction could be the combination of carbon dioxide and water vapor, and this is going to form carbonic acid. And notice here that the equation is balanced. What do we mean that it's balanced? You find the same number of atoms on both sides. There's one carbon on each side, there's 2 hydrogens on each side, and there's a total of 3 oxygens on each side. How do chemical reactions occur? Well, a lot of things need to happen, but most importantly, there needs to be a source of energy. And in most systems, you have thermal energy from the environment, and this can help convert, for example, liquid gas into liquid water into water in the form of gas. So we have 2 types of reactions. We can have endothermic reactions or exothermic reactions. Endo means in, and thermic means energy. It must absorb thermal energy for the reaction to proceed. In exothermic reactions, exo means like exit. Energy is being released, so it releases thermal energy. In this figure 2.17, it shows you the movement of energy and in an open, closed, or isolated system. So what is energy? Energy is the capacity to do work or to supply heat. And there's really 2 ways of looking at it. There's stored energy, there's stored potential energy, or there's kinetic energy. So when I think of potential energy, I think of position. When I think of kinetic energy, I think of motion. And I always think of sumo wrestlers. Sumo wrestlers are in motion and they have a lot of energy and heat. So there are 2 types of energy, potential and kinetic energy. Potential energy, objects gain or lose ability to store energy due to its position. For example, if I were to lift up my book and lift it above my head, it would be gaining potential energy, but the minute I drop it, it's going to lose its potential energy. We can also have potential energy in the bonds. In covalent bonds, the position of the shared electrons is a form of potential energy. Shared electrons are far from the atom's nuclei, and they're typically long and weak. And electrons can also shift closer to one another and become shorter and stronger. So these are different forms of potential energy in covalent bonds. It is also known as chemical energy. So chemical energy and potential energy are the same. So here are different forms of potential energy found in electron sharing. In oxygen-hydrogen bonds, you have short, strong bonds, and then at the opposite end in carbon-hydrogen, you have long, weak bonds. So in nonpolar covalent bonds, you have increasing potential energy. Thermal energy is also kinetic energy, and the energy of motion creates a lot of heat. So temperature is a measure of thermal energy in a molecule. Cold objects have low temperature, and therefore their molecules move very slowly. Heat is a measure of thermal energy being transferred between two objects. Energy can also be described by the first and second laws of thermodynamics. In the first law of thermodynamics, it says that energy is conserved, it cannot be created or destroyed, and it can only be transferred or transformed. Energy transformation is at the heart of chemical evolution. We had to have these energy transformations to create larger and more complex molecules. So that was exposure to massive inputs of energy. Kinetic energy in the form of heat was present and in gradually cooling molten mass that formed this planet. Chemical reactions are spontaneous if they proceed without any continuous external influence. In other words, no added energy is needed. That means the products have lower potential energy than the reactants. The products are less ordered than the reactants. That means that there's greater entropy. So that's a new word. What is entropy? Entropy means disorder. When you have a spontaneous reaction, it means that the products have less order and less potential energy. In other words, it's going from a big molecule to a small molecule. Small molecules have fewer bonds and less order and greater disorder or greater entropy. In this reaction, it shows that we start off with glucose in the presence of oxygen. In fact, this is respiration. And in the presence of oxygen, glucose is broken down into water and into CO2. Notice how large glucose is. Glucose is highly ordered. It has a lot of bonds. It has a lot of potential or chemical energy. It's broken down into small molecules with very few bonds, and so it has higher disorder or higher entropy. So this would be a spontaneous reaction. Another type of spontaneous reaction is hydrogen gas and oxygen. Notice here there's a shift in electron from nonpolar to polar covalent bonds, and this shift in electrons increases entropy. So potential energy drops, creating a spontaneous reaction. The second law of thermodynamics states that entropy always increases. In other words, disorder is always increasing. And a classic example is the Hindenburg, like what we saw right there. Is that when you see an explosion of hydrogen gas, that is an increase of entropy. Physical and chemical processes proceed in the direction that results in lower potential energy and increased entropy, or both. Okay, so what is chemical evolution again? It's the movement of molecules from small to larger, more complex. In 1953, Stanley Miller and his graduate students actually performed a classic experiment, and they showed that complex molecules could be formed from simple molecules. In other words, showing chemical evolution. They did the classic example here. This looks like a Frankenstein. This would be an experiment in one of the old-fashioned Frankenstein movies. You see two globes. The lower globe represents the ocean, and the upper globe represents the atmosphere. And when they initially did the experiment, they put very simple molecules in the ocean, and they heated it to cause evaporation and condensation, and when they did, nothing happened. But the minute that they added the electrodes, huge amounts of energy into the system, they saw that from simple molecules, larger intermediate molecules could be formed. And you can see that in the frame below. And the ocean, its color turned from clear to a reddish color, indicating a change in reactions. Miller's apparatus showed that complex molecules could be formed from simple molecules. And these simple molecules contained amino acids, and amino acids are the building blocks of proteins. Now, this is important because most organisms are mainly made of proteins. So, in this experiment, they concluded that chemical evolution occurs readily if simple molecules with high and free energy are exposed to kinetic energy. The last part of this chapter talks about carbon. Carbon is the backbone of all organic molecules. Except for water, almost all molecules found in organisms have this atom. And the reason is because if we look at its valence shell or its outermost shell, we see that there are 4 electrons, so it can form 4 covalent bonds. So it has a valence of 4. And so it's many types and shapes of compounds can be formed. So therefore, all organic compounds contain carbon bounded to other elements. And we have a limitless array of molecular shapes. And we can have single, double, or even triple bonds. There are some examples here of octane and glucose. So let's take a look. So on the left-hand side, we have octane. This is what you would find in gasoline. Notice the carbon backbone and hydrogen coming off from the sides. On the other side, we have glucose, and glucose is in a ring, but notice that the backbone of this ring is still made of carbon, and coming off of the carbons are hydrogen and hydroxyl groups. So there's different types of functional groups, and you have to be aware of these functional groups because now we're going to go from small molecules like water or methane to really large ones like proteins. So the only way that we can understand their behavior is by looking at the functional groups. So some of these functional groups are amino groups, carboxyl groups, carbonyl groups, hydroxyl groups, phosphate groups, and sulfhedryl groups. And if you look in your book at table 2.3, you can actually have a clearer picture of each of these functional groups. Small organic molecules assemble into large molecules. Remember, it requires vast amounts of kinetic energy. But to make macromolecules, they're actually made from small subunits called monomers. Another way to say a macromolecule is a polymer. And to create a polymer, we do it via polymerization, or the linking of these small monomers together. So monomers are the building blocks of polymers, and a polymer is another way of saying macromolecule or large molecule. So here we see a lot of monomers linked together to create a polymer, and this is called polymerization. So polymerization is created through condensation reaction. So what is a condensation reaction? Another name for it is dehydration reaction. And this is formed when water is released. There's a loss of water and two monomers are connected with each other. The opposite of a condensation reaction is hydrolysis. I always think of hydrolysis, water breaking. Water moves into the bond and actually breaks the bond. So in a condensation reaction, water is leaving the bond, creating one, and for hydrolysis, water is entering the bond and breaking it. I love figure 2.24. It shows here that water is released when a bond is formed between two monomers. In a hydrolysis, the opposite is true. When water moves in, then it breaks the bonds between a monomer. Hydrolysis increases entropy. Does that make sense? Yes, because hydrolysis is breaking bonds and making small molecules out of a large one. Is that increasing disorder? Yes, it is, because small molecules with fewer bonds have greater disorder. This is the end of chapter 2.